podcast, BalamSemiconductor. Episode 1, From Text to Chip, the role of RTL in digital integrated circuit design. Welcome to BalamSemiconductor, the podcast where circuit design comes to life. I'm Carlos Alberto, and in this first episode, we're going to dive into the fascinating world of digital design using Verilog HDL. If you've ever wondered what powers a processor or a chip, you're in the right place. Let's begin with a fundamental question. What is RTL, and why is it so important in the semiconductor industry? RTL stands for Register Transfer Level, representing a key stage in the design of digital circuits. Companies like ARM, Synopsys, and Cadence have built entire ecosystems around this stage because it defines the internal structures and architectures of the chip. At this point, designers use languages like Verilog to model the behavior of hardware before it physically exists. Depending on whether the final design will be implemented in an FPGA or an ASIC, the workflow that follows changes significantly. RTL allows us to describe circuits in terms of registers, clocks, and combinational logic. Think of registers as small memories that store data. With every clock cycle, data moves from one register to another, potentially passing through logic blocks that perform operations like additions, comparisons, or bit shifts. This approach enables engineers to structure their designs with precision and scalability. Verilog is a hardware description language. It's similar to the C programming language, but tailored for digital circuit design. Rather than describing sequential instructions like in software, Verilog describes connections, signals, and events that occur in parallel, just like in real hardware. Circuits in Verilog are organized into modules, each with inputs and outputs, and may include internal signals such as wire or reg. This modular approach makes it easy to build reusable and hierarchical designs. Let's look at a classic example. Imagine you want to turn on an LED permanently. In Verilog, you can write a simple module called Hello World that sets the output to 1, like this. Module hello_world LED. Output LED. Assign LED equals 1 foot B1. End module. To verify this design, we use a test bench, which is a separate file that simulates the environment of the module and allows us to check if the LED is indeed turned on during simulation. You can try this example online using the EDA Playground platform. The link is included in the episode description. Here's an important clarification. Designing for FPGA is not the same as designing for ASIC. Although both use Verilog and start at the RTL level, the backend stages diverge. For ASICs, once the RTL is done, the design goes through logic synthesis, timing analysis, and physical verification before being manufactured in silicon. In contrast, FPGAs go straight from RTL to device programming. Understanding this difference is crucial when selecting tools, applying constraints, and choosing design strategies. That was BalamSemiconductor. Today, we learned what RTL is, why it matters, and how Verilog enables us to build our very first digital hello world. If you enjoyed this episode, subscribe and share it with your community. In the next one, we'll explore how to create combinational and sequential logic using Verilog. Until then, keep thinking in hardware, because digital circuits are built with HDL.